All right, let's jump right in. Today, we're going to pull back the curtain on a really powerful data science technique. It's all about discovering hidden patterns and structures in data, and it's called clustering. It literally helps us find meaningful groups that we never even knew were there.
So, have you ever wondered how services like Netflix or Spotify do their magic? They're always recommending things to people who watch X. But think about it. They don't start out knowing who those people are. They have to find that group first. And that's the core challenge we're talking about, finding meaningful groups when you have no labels to start with.
Well, the answer is a technique called clustering. Now, unlike a lot of other methods, clustering is what we call unsupervised. That means it doesn't need any pre-labeled data to work. It just dives in on its own to find these hidden structures, grouping similar things together automatically. It's pretty much the secret sauce behind a ton of the personalization you see every single day.
Okay, but before we can tell a machine to go find a good cluster, we have to define what good even means. And really, it all comes down to two simple golden rules.
First up, you have cohesion. This just means that everything inside a single cluster should be really tightly packed together and super similar. Think of a tight-knit circle of friends. The second rule is separation. This means that different clusters should be far apart from each other. They should be distinct, kind of like separate circles of friends scattered across a room. High cohesion and high separation, that's the gold standard.
To put it as simply as possible, the whole goal is to make sure that the members of any one group have way more in common with each other than they do with members of any other group. That single idea is the engine that drives the entire field of cluster analysis.
But here's the thing. Hitting that goal isn't always so straightforward. There's more than one way to group things, mainly because data doesn't always come in nice, neat little packages. This means data scientists need a whole toolbox of different approaches to get the job done.
One of the most common tools in that toolbox is center-based clustering, and the famous K-means algorithm is the perfect example. The logic here is really intuitive. You're trying to find a center of gravity, or a centroid, for a potential group, and then you just assign all the nearby data points to it. This works brilliantly when you're expecting to find these dense, kind of ball-shaped clusters in your data.
But what if your groups aren't shaped like spheres? What if they look more like a winding river or a crescent moon? This is where a completely different philosophy comes in, density-based clustering. Instead of looking for centers, algorithms like dbScan look for crowded neighborhoods of data separated by empty space. This is so powerful because it can find these complex, weird-looking shapes, and it's also fantastic at spotting outliers, which it just labels as noise.
And believe me, these are just two examples. The data scientist's toolbox is just overflowing with a huge variety of algorithms, hierarchical, spectral, you name it. And each one has its own unique way of defining and finding groups. And all this variety leads us to a really critical question. With all these different methods out there, how in the world do we know which one did the best job for our specific data? How do we pick the right tool? I mean, this is the central challenge, right? Without a predefined right answer to check our work against, how do we actually grade the results? We need a way to score the quality of the groups that each of these algorithms finds.
And the solution is to use what we call validation metrics. Honestly, the best way to think of these is just like a report card for our clustering results. They give us a hard number, a quantitative score, for how well each algorithm did based on those principles we talked about, like cohesion and separation.
For example, the silhouette score basically asks each data point, hey, are you happy in your current group, or do you feel like you belong more with your neighbors? A high score means everyone's happy where they are. The Dunn index is even more direct. It's just a ratio of how far apart the groups are versus how spread out they are internally. And entropy measures how mixed up the groups are. Pure, distinct groups get a low score, and that's exactly what we want.
Okay, so that's the theory. But how does this all work in practice? Let's look at a real-world case study where researchers used these very techniques to analyze a telecom company's customer data. They were looking for hidden patterns to explain why customers leave, a classic problem we call customer churn. The process they followed was really methodical. First, they took all the customer data. Then they ran not one, but 9 different clustering algorithms on it. After that, they used their report card, those validation metrics, to score every single result. Finally, they picked the winner and really dug into the clusters it found to see what story they could learn. So, after running 9 different algorithms and scoring them all, which one came out on top? The winner was spectral clustering. And this wasn't just a gut feeling.
The report card was crystal clear. It earned the highest scores on key metrics like the Dunn index and entropy, proving it was the best tool for finding the specific kind of structure hidden in this particular dataset.
So what was the big insight? What did spectral clustering actually find hiding in the data? Well, it uncovered these distinct segments of customers who behaved very, very differently when it came to their likelihood of leaving the company.
And this chart illustrates the payoff perfectly. The model found one group of customers, we'll call them Cluster 1, with a churn rate of about 14%. But it also found another group, Cluster 2, where the churn rate was 28%. That's exactly double. These were the high-risk customers hiding there in the data the whole time.
And that discovery is incredibly valuable. So why does this matter? Because now the telecom company doesn't have to guess. They can design a specific campaign, maybe with special offers or extra customer support, targeted directly at the high-risk customers in Cluster 2 to convince them to stay. This is how abstract data patterns turn into concrete business decisions that can save millions.
So you see, clustering isn't just about finding circles on a chart. It's about uncovering hidden realities in our data that can lead to smarter decisions. It really makes you wonder, if you could use this tool to find any hidden pattern in the world, what would you look for?